We know that absorbing chains do not have steady-state probabilities, but they have some certain kind of steady-state conditions, and that is what we're going to talk about in this video. So let's start. Many organizations employ S categories of workers, so there are several categories. In the example that we've seen before in a law firm, there are juniors, there are seniors, and there are partners. Even though people coming into the law firm and then leaving the law firm, which makes that problem as can be modeled as an absorbing chain, but it is useful to be able to model as well how many people will exist in each category of the worker in a steady state. So after considering people who enters the firm and then leaving the firm, we would like to find how many juniors we have, how many seniors we have. So that's what is called as the steady state census. It exists if for each category we may find a number that is kind of stable. So N1 is the number of employee of category 1, N2 is the number of employees of category 2, up to the number of employee for category S, which is denoted as NS. If steady state census exists, it means that the number of groups member stays the same all the time. And to have that kind of condition, we need to fulfill this condition. The number of people entering group I must equal to the number of people leaving group I during each period. And this makes sense, right? Because if you want to keep the same number of members of a group, it means that the number of people who enter this group must exactly the same with the number of people who are leaving the group. If that's not the same, it means that the number of members of your group might be shrinking, might be getting larger, so it will not reaching steady state. Again, to reach steady state, the number of people entering the group must exactly be the same or replacing the number of people who are leaving the group. Here's an illustration. You have several groups and then the number of group is denoted by N. So Ni is the number of people in the group yellow. So we have people enter the group yellow in this period. Let's denote it as Hi. And then we have also people who enter the group yellow from the other group. So from the red, green, and blue, we have a portion of each group that enters the group yellow. So those are the people who enter the group yellow in this period. To keep the number of members of the yellow group stays the same, we need to make sure that all those people who enter the group of the yellow is exactly the same with the number of people leaving the group. So some people leave the yellow group to go to the green, some people go to the red, some people go to the blue, and the amount of those who enters must equal with those who are leaving. Okay, so this equation shows the balance in group I, which is illustrated in the previous slide. So let's see what this equation means. The left-hand side is about people who enter group I. So the people who enter group I may come from outside. So we just hire some people and then they will enter group I directly. People who enter group I may also come from other groups. So we have all other groups K, and then each of the group K has the number of member NK, and then part of them, a portion of them, denoted as PKI, will enter group I. So PKI is the fraction of group K people moving to group I. And both the people that we hire and then those who move from the other group must equal with people who leave group I. So people who leaves group I equals to the portion of group I people that moves to group K, and then we take the sum for all possible K. So Ni is the number of members in group I, and then Pik is the portion of people of group I that moves to group K. Let's apply the steady state census to this example. Suppose each American may be classified into one of the three groups: children, working adults, and retired people. During 1 year period, 0.959 of all children remain children, and so on. And all this information may be summarized into this transition probability matrix. So the first row is children, working adults, and then retired people. The fourth row should be those who died, but it is not represented in this matrix. The probability should be 1 because dying is an absorbing state, right? After somebody died, the person is always in the status of died, right? Okay, so the column 1 is for children, working adults, retired people, and died. So that is the transition probability matrix, and then from this sentence we know that 100 people enters the world as children every year, so H1 is 1,000. Sorry, I said 1,000 children born each year, so H1 equals 1,000. And then no people enters the world suddenly as working adults or as retired people, so H2 and H3 equals 0. So the question is, we need to determine the steady state census. Now let's compute the steady state census for each of the group using this equation, saying that people who enter a group must equal with the number of people leaving the group. And then we denote N1 is the number of children, N2 the number of working adults, and N3 equals the number of retired people. So we use this equation for each of the group that we have: children, working adults, and retired people. The left-hand side is about the number of people entering group I each year. So for children, we have 1,000 children coming into the world every year. And then from the transition probability matrix, we can see that working adults cannot return to become children again. Retired people also cannot return to become children again. So the only thing that may enter the group of children is from those who are born into the world, so H1 only. But then from the children group, 0.04 may leave the group to become working adults, and then 0.001 may leave the group because they die. So those are this number multiplied by the number of children group, which is N1, the number of the member of the children group. Now for the working adults, we do not have those who are born as working adults immediately. So we only have the entrance from children to working adults. So 0.04 times N1, because N1 is the number of children. So 0.04 of children will enter the group of working adults each year. And then from working adults, 0.03 will leave this group because they retire. 0.01 will leave this group because they die. So those are this number multiply with N2, which is the number of working adults. For retired people, the entrance to this group comes from working adult. So working adult enters the retired group. As many as 0.03 of the working adults must equal those who leave the retired group because they die, 0.05. And then we solve these three equations, and then we will get the solution of the numbers of N1, N2, and N3. So this is the steady state census for this problem. The second question is that if each retired person receives a pension of $5,000 per year, and then it is funded by payments from working adults, how much money must each working adult contribute to pay that pension? Well, first we need to compute the total pension. So we pay 5,000 for each retired people, and then we know that in the steady state there are this many retired people, so this is the amount of total pension that we have to provide each year. And then we know that we have this many working adults, so we divide that amount with the number of working adults, and it's approximately each working adult needs to pay 3,000 a year to support the pension of retired people. Now we go back to the example of the law firm that we have seen in the previous video. Here we have the same transition probability and everything, but now the question is, the firm wants to have 50 junior lawyers, 30 senior lawyers, and 10 partners in the long term. So they would like to have this fixed number of juniors, seniors, and partners, or steady state numbers. So the question is, to achieve those steady state numbers, how many lawyers of each type should Mason and Berger hire each year? So in this case, we have already known the N, and then we are asked about the H, H1, H2, and H3. Now, because leave as non-partner and leave as partner, they are both absorbing chain. And then in the steady state census, we don't really care with the absorbing chain, like the person who died in the previous example. We may just combine them together into one state, and then we do not write that state in the row. So the first column is junior, second column is senior, the third one is partner, and the last column is leaving either as non-partner or as partner. And then for the row, this is junior, this is senior, this is partner, and we do not write the leave as partner or leave as non-partner in the rows. And then from here, from the example, we know that this is what we want to achieve, N1, N2, and N3. And then we are asked about H1, H2, and H3. To answer this, we use the same sets of equation for each of the type of the workers, but now instead of having N as the unknown, we have H as the unknown. And all this equation means the same as before. For example, let's take a look at the second row, senior. So those who enter the senior group is the one that we hire as senior, H2. And then we also have the entrance from here, junior who moved to senior. That's why 0.15 times the number of junior that we have, which is 50, right, equals to those who leave the senior. So those who leave the senior group is 20% plus 10%. So we have 0.20 plus 0.10 times 30, which is the number of senior group. And then if we solve these three equations, we will get the answer that we need to hire 10 juniors every year, 1.5 seniors every year, and then minus 5.5 partners every year, such that we will achieve this steady state number. Now here's the question. Steady state census does not exist because H3 is negative. Is this statement true or false? I will give you the answer after the pause on the video. The answer is false. Steady state census exists in this case. Actually, it is given in the problem that these are the number of each group that we would like to achieve in the steady state. H3 equals minus 5.5 simply means that to achieve those numbers, we need to fire 5.5 partners each year. I agree that in practice this is difficult because you just cannot fire half of a person, right? But theoretically, that is the number that you need to do to achieve the steady state numbers. Okay, so that's the end of all topics that I like to talk about in Markov chain. So thank you.